Hi again, this video is on Euler's method. Euler's method, and this is for approximating values which are of a solution to DEs. Bit confusing there. I didn't say that very well. Let me explain. So what this method is all about is, say we have a graph. It looks like that. Then what Euler's method does is it says, well, if we can't solve an integral or something like this, and we can't do that, what we can do is approximate the curve. In other words, if you take a point, any point that's on this function, and then you draw a tangent to that point. I chose a bad point. Can I choose a better point? You'll forgive me, won't you? Let's say we choose this point here. And if we draw a tangent at that point, oh, that is just the worst tangent ever. I'll do it fast. Better if I do it fast. Okay, if we do that tangent, so there's our first point. Let's call that first point x0. And if we move that along, let's move that forward by h, some small gap by h, then we get this next point here. And what we're doing there is we're approximating this curve. Okay, so that's the next point which approximates the curve, and so it's off by sort of that much. And what we can do again is, let's do it again. And so at this point, what is the tangent? The tangent line is like sort of like that. And so if we move forward by h again from there at that sort of same derivative, then it sort of go, I'll try to make it parallel, sort of goes like that. If we move it along by h, then our next approximation would be there. So what we're doing, in other words, we're looking at what the slope of the curve is at a certain point, and we're moving it forward by h. So again, if we move to our next h, so we're going to here, what's the slope there? It's sort of like in there, so I'll draw sort of like the slope approximately of where it is there, and I move forward by h, and there's my next approximation point. I'll do it again here. What's your gradient equal to? It's roughly that, so I'll sort of draw it in there, sort of goes like that, and so your next point h will be roughly there. And you can see it's approximating the curve. It's not exactly it, it's only approximating. And so again, gradient here. What's the gradient? It's sort of roughly like that. So it'll be again like that. If we go forward by h, the next point will be there. Let's do that point there. The gradient is equal to sort of roughly going up a bit, sort of like that. And so the next point will be there. And so what you'll see is that the approximation to this curve that Euler's formula gives us is the following. It starts here and it sort of goes like this. Oh, I'll press that wretched button again. So it goes like that. So that's just, the blue is the approximation of the function y. Okay, yfx. And so that's what Euler's method does, and I'll explain it more in class. But what happens is that looks pretty inaccurate, doesn't it? But what happens is, as h gets very small, then that gets more and more accurate. That's getting closer and closer to the function for very small. So by very small, if you had h was equal to 1 unit or something like that, that's generally considered to be quite bad. If h was equal to 0.1, that's actually pretty good. It gets pretty tight. The smaller that h gets, the better it gets. Okay, and so the reason we do this is because we can't solve differential equations. There's many in the world that are impossible to solve, and so what this is just an approximation. It's a very good approximation, and we can use computers and calculators to compute values of y when x is equal to a certain value, and we can use we just keep, what we do is we just set a very, very small value of h and just keep going and going and going and going, keep increasing h until we get to the value that we want. If that's the point there where we know the x but we want to know what the y value is, then we just keep increasing it until we get to that value. And I'll show you the formula now. I hope that made sense. It's quite a confusing way to explain it. I'll do it better in class, I promise. And so what it says is that if you have a differential equation, dy by dx is equal to some g x of y. In other words, some function of x and y. It might not have y in it all, it might just be g, but it might just be x, sorry. But I'll write that down. And if you start from some value, your initial x0 and y0, that's where you start from, then what happens is that your xn plus 1th term will be equal to the previous term xn. And remember how we jumped xn, we moved forward by h, whatever the h value. What we're going to do is add h to that. So x is just getting increased by h at a time. So h is called our step size, how far we're moving to the right each time. And remember, the smaller the step size, the more accurate your results will be. What happens with the y value? The yn plus 1th term will be equal to the ynth term plus h times g of x and y, like that. And so there, that's Euler's, all of that. I was trying to do that in red. That is Euler's method. And there's all these fancy things in your textbook about putting into calculators and programs and writing all these things and doing various crap. But in the end, what the course requires you to do is to be able to apply Euler's method in a couple of steps. And I'll just show you what I mean. Okay, so let's just go to an example. I'll try to fit it on one of this page so you can have this here while I'm doing the answer. Okay. So we want to use, so if we've got something like this, dy dx is equal to cos x, and we're given that x0 equals 0 and y0 equals 1, then we'd like to find y, it says y3 in the example, I'm just going to get y2, less work. Using a step size of 0.1. Okay, so let's have a look at what this means. This is the DE that we can't solve, but we could solve this, but they get more complicated than this. We can't solve that. Initially, we start where x is equal to 0, y is equal to 1. That's our first point. If you think about the graph, that's the first point on the curve that we're going to start from, and then we're going to move to the right by 0.1 at a time and find the value of y2. So let's do this. Okay, so I was trying to squeeze it in. So x1 will be equal to, so xn plus 1, that'll be equal to x0 plus h, which is equal to, what was x0? That was 0. What's h? It's 0.1. So that's equal to 0.1, and that makes sense. In other words, x just gets bigger by 0.1 every time. Okay. Yeah. y1. Let's find out what y1 is equal to. y1 is equal to y0, following this up here, plus h g x 0 y0. Okay. So we're just doing the previous numbers. Doing those, okay, so that's equal to, the y is the hardest one to find out, of course. y0 is equal to 1 plus h 0.1, and all we're doing is putting x0 and y0 into this formula here. So it's going to be cos of x0 is 0, so that's that there, okay, and we just need to evaluate this. Cos at 0 is equal to 1, and so that's equal to 1.1. So what this tells us is that an approximate value of this particular function, the solution to this particular DE here, that when x is equal to 0.1, y will be approximately 1.1. Okay, so these two go together. When x is equal to 0.1, y is approximately equal to 1.1. Okay, now we're asked to find y2, so let's keep doing that. x2 is equal to x1 plus h, so we just keep on adding 0.1, so that's equal to 0.2. y2 will be equal to, look at the formula, y1 plus h g of x1 and y1, okay, equals, right, what was y1? y1 was 1.1 plus h is 0.1, and putting in, that's a very loud ring. I'll just wait for Tanya to pick that up, so I'll keep talking. X1 was, what was X1? X1 was 0.1 up here, so we need to substitute that in. So in here, that'll be cos of 0.1. Okay, and so what you do is again, we don't know how to do cos 0.1, put that into your calculator, and you get 1.1 plus 0.1 times that, and you'll get some value. And cos 0.1, it'll be slightly less than 1, and so that'll be that. So it'll be, just as a guess, 1.19 or something like that. Let's just go with that. You'll check that in your calculator at the time. So so there's y2, so our x2 value there, and our y2 value here. And so what this is saying is that so we've got some point, when x is equal to 0.1, y is approximately equal to 1.1. This next lot of values here is saying that when x is equal to 0.2, y is approximately equal to 1.19. Okay, so something like that. So this is what it's saying. Hopefully you understand that. Sometimes the question will ask to find y2. Sometimes it will ask to say find the approximate value of y when x is equal to 0.2 or something like that. And so you need to find the corresponding value of 0.2. And so you need to do it 2 steps, because it's 2 lots of 0.1 you need to find. So that's a quick example. Hopefully that makes sense, and I'll give it to you more in class.